O professor Príamo Melo, coordenador do Programa de Engenharia Química. E a professora Lavínia Borges, da diretoria da COPPE. E agora eu passo a palavra para o professor Cláudio Habert.
Muito obrigado. Dá para ouvir bem? Então, falar com essa máscara é uma tortura, mas é uma necessidade. Então, prezados representantes da instituição, bom dia a todos, né? Sou Príamo, coordenador do PEC, professora Lavínia, diretora acadêmica da COPPE. Devo mencionar que representantes da reitoria da decania não puderam comparecer por motivo de força maior. Em particular, a professora Verônica, que viria representante da reitoria, pegou Covid ontem, então, lamentavelmente, não poderá estar presente, mas mandou todos os desejos de um bom evento. Então, caros colegas presentes, prezados alunos, em nome da comissão organizadora, em particular, professores Henrique Pacheco, João Paulo e Maurício Bezerra, tenho a enorme satisfação em dar-lhes as boas-vindas por mais essa versão que já se tornou um tradicional encontro no âmbito da UFRJ. Devo mencionar que esse mês ocorre no país e na UFRJ uma série de eventos ligados à divulgação de ciência e tecnologia. Em particular, essa semana na UFRJ, a nossa universidade está sendo visitada por centenas de estudantes circulando no meio acadêmico e tendo uma ideia de como eles poderão planejar uma carreira profícua nessa universidade em ciência e tecnologia. Então, o nosso evento se inscreve também nessas atividades. Essa comissão foi formada no final de 2019. Vejam, um recuo no tempo, né? E a gente planejava para 2020 a organização do 20º Colóquio PEC, que ia coincidir com os 100 anos da UFRJ. Então, tínhamos grandes planos, as coisas iam se desenrolar com um ânimo enorme, mas, infelizmente, apareceu a pandemia e tivemos que adiar por 2 vezes esse evento. Enquanto todas as atividades ocorriam de modo remoto, nós decidimos, esse ano, apesar de tudo, fazer de modo presencial. Eu acho importante agregar as pessoas e retomar as atividades como devem ser retomadas. E eu quero também comentar que, ao longo desse ano que passou, nós celebramos 100 anos da UFRJ, o que é altamente significativo para um país com um passado colonial como o nosso. Isso aqui é... Bom, a comissão, junto com o Programa de Engenharia Química, manteve-se mobilizada ao longo desse tempo, alerta ao cenário que nos circundava e procurando captar, nos seus devidos momentos, os sinais que apontavam para as expectativas da nossa comunidade. Com a retomada das atividades presenciais da UFRJ em 2022, foi decidida a realização do evento, o que nos traz ao momento atual, que tem significados absolutamente especiais. Principalmente para as novas gerações, queremos assinalar 2 aspectos, um de natureza estrutural e outro de natureza conjuntural. Vamos aos detalhes. A estrutura versátil do colóquio, todo ano que a gente fez esses 20 colóquios, cada ano tem suas características. Dependendo da comissão e do momento, organizamos as atividades de várias formas. E todas elas são voltadas para cumprir os objetivos do colóquio. Então, consolidando ao longo desses 20 anos de sua vigência, estando o PEC aqui na COPPE, no limiar dos seus 60 anos, ano que vem o PEC vai fazer 60 anos de existência, junto com a COPPE. Então, é uma data extremamente auspiciosa. O Colóquio procura mobilizar em sua comunidade no sentido de reforçar a importantíssima identidade institucional, ou seja, vestir a camisa. Toda a comunidade precisa ter esse sentimento de pertencimento. E o Colóquio procura reforçar isso. De que forma? Promove uma integração geracional entre todos os membros. Quer dizer, o fato da gente se reunir e participar de várias atividades promove esse encontro. E isso que o Colóquio procura realizar. E, ao mesmo tempo que a gente vai lembrando prêmios, conquistas, resultados obtidos pelos seus pesquisadores, o Colóquio é uma oportunidade ímpar para divulgar para fora dos muros do PEC e da COPPE o que se faz aqui dentro, atraindo novos colaboradores e atraindo novos talentos. Então, são multipropósitos que a gente pretende. Além disso, por outro lado, os conferencistas debatedores que são convidados para proporcionar às audiências aqui reunidas, incluindo alunos de graduação, cursos de curta duração inéditos, apresentações de tópicos de fronteira da engenharia química e a discussão de temas críticos da atualidade brasileira, como todos os que foram selecionados na programação desse ano. A comissão teve o cuidado de pegar temas realmente gerais e que traduzem o ambiente atual pelo qual passamos. Bom, o segundo aspecto, que é conjuntural, que a gente queria ressaltar, é o momento especial que atravessamos e que talvez não tenha tido paralelos na história. História curta da instituição, história curta do país. Mas, de minha lembrança, não me lembro momentos tão críticos e agudos como os que estamos atravessando agora. Os que nos acompanham há mais tempo, refiro-me aos pessoal que tem mais quilometragem aqui, deixa eu tirar esse óculos, que o embaçamento aí é impiedoso, né? Então, os que nos acompanham há mais tempo sabem dos ciclos virtuosos que a pós-graduação e a pesquisa científica e tecnológica e a própria inovação, entendida no sentido restrito e no sentido amplo do termo, passaram em tempos recentes, com investimentos em todos os setores das cadeias produtivas e que permitiram saltos quantitativos e qualitativos invejáveis. Eu estou lhes dando aqui o testemunho de uma longa carreira na COPPE e o que aconteceu ao longo dos decênios recentes. Isso foi acompanhado de uma melhoria da qualidade de vida da população brasileira. Tudo isso foi desacelerado pelas circunstâncias políticas que marcaram o país nos últimos anos e que não podem ser atribuídos exclusivamente à pandemia. Entre outros desmandos, testemunhamos e fomos vítimas de uma gradual redução dos orçamentos dos órgãos financiadores de educação, pesquisa, desenvolvimento e inovação, isso sem falar das deliberadas políticas de descrédito da ciência e, por conseguinte, de todas as atividades a que ela está atrelada. Em consequência, vimos crescer sentimentos de desesperança em milhares de jovens ávidos por uma melhor educação e oportunidades de emprego. Em novembro de 2022, o 20º Colóquio quer celebrar com vocês hoje uma inversão do sinal da derivada, para usar a linguagem matemática. Queremos crer que novas condições foram criadas no país para retomar políticas públicas consequentes, em particular em ciência e tecnologia, e que contemplem adequadamente setores estratégicos, como óleo e gás, saúde, meio ambiente, energia alternativa, inteligência artificial. A lista é longa, e o nosso desafio é priorizar alguns desses temas. Sabemos que não será fácil, mas que a universidade, a COPPE e o Programa de Engenharia Química estarão sempre disponíveis para colaborar nessa direção. Através de um painel bem variado e geral, o 20º Colóquio de Engenharia Química quer voltar a criar confiança nas jovens gerações, arregimentando a sua generosidade e relembrando o enorme potencial que o país dispõe. Gente capacitada, energia renovável, terra, sol, matérias-primas, um parque industrial a ser recuperado, um mercado interno invejável. A lista dos fatores positivos que nós temos é enorme. Então, temos todas as condições de retomar essas atividades e ter a participação das novas gerações. Bom, muito boa-vinda a todos. Esperamos que aproveitem as oportunidades. E quero lembrar que há uma bela festa de confraternização que nos espera no final desse evento, onde esperamos encontrar todos vocês. Bem-vindos e bom proveito no colóquio.
Obrigado, professor Cláudio Habert, pelas palavras. E agora eu passo a palavra para o professor Primo Albuquerque.
Bom dia a todos, bom dia. Sim, eu escrevi também um pouquinho para não me perder. Primeira coisa que eu queria dizer, uau, né? A gente está celebrando hoje, iniciando hoje, o 20º Colóquio Anual de Engenharia Química, do Programa de Engenharia Química aqui da COPPE. É uma grande honra para mim estar presente aqui hoje, nessa mesa, com o Habert, com a Lavínia. Eu devo confessar que muitas memórias surgem naturalmente nesse momento. Eu participei, por exemplo, de todas as edições do colóquio. Isso é um dado já significativo. O colóquio começou enquanto eu era... a semente do colóquio foi plantada na época que eu era aluno de doutorado. Ele foi chamado de DIAPEC. Alguns anos depois é que ele virou oficialmente colóquio anual, e eu já estava aqui como professor. Eu completei este ano 20 anos como professor da UFRJ. Então, eu mesmo já fui organizador do colóquio em duas edições. Então, desses 20 aí, 10% está na minha conta aí, tá? A de 2005, alguns de vocês estavam já, assim, acho que acabaram de sair da creche. Em 2005, juntamente com um grande time de alunos, e depois, em 2018, juntamente com a professora Márcia Desotti, que não está aqui com a gente hoje, infelizmente, está no congresso no Peru, e também outro grande time de alunos, sem contar com a valiosa participação da secretaria e de tantos colaboradores que terminam se juntando na organização dos colóquios. O nosso querido colóquio sempre foi desenhado com carinho por seus organizadores, nessa missão nobre de compartilhar com a sociedade, com a indústria, com nossos pares, os nossos achados científicos, bem como a visão de grandes palestrantes e professores que já nos deram a honra com a sua presença. Exatamente como na 20ª edição, não é diferente, tá? Esta edição tem um diferencial, é o retorno do colóquio, depois de uma pausa de 2 anos, devido a uma implacável pandemia de coronavírus, que nos assombra e até hoje está escondendo aí os nossos rostos, né? Até ontem, eu estava observando, eu mandei uma mensagem para vocês exatamente sobre esse assunto, transmitindo mensagens que chegam na reitoria dos grupos de trabalho do Covid. Então, o que nós temos para esse ano é uma incursão no futuro. É um tema absolutamente pertinente nesse momento que passamos, com dificuldades, como o Habert falou, bem conhecidas no campo da educação, da ciência, da geração do conhecimento. Tá? Até mesmo uma rápida inspeção na programação deste evento, percebemos me permitam a comissão organizadora, a ousadia da comissão organizadora. Da origem da vida, a inteligência artificial, das partículas subatômicas, a transição energética, vinham cristalização, dinâmica de fluidos, poluição e empreendedorismo, enquanto, ressalte-se, acontece agora, nesses dias, nessas semanas, a 27ª Conferência do Clima, COP27, da ONU, no Egito. Então, eu parabenizo a comissão organizadora por uma curadoria meticulosa, criativa, inspiradora e cativante dos assuntos que estão colocados aí para vocês na programação. Eu desejo que vocês todos usufruam dessa oportunidade que lhes é apresentada, que saiam daqui muito curiosos, muito mais curiosos, indagadores, críticos, porque a gente sabe que inteligentes, muito inteligentes vocês são, né? Então, vejam, tudo que precisamos decidir é o que fazer com o tempo que nos é dado. Quem escreveu isso aqui foi o John R. Tolkien, né, que eu adoro, O Senhor dos Anéis. Então é isso, gente. Aproveitem e muito obrigado pela oportunidade de estar aqui hoje.
Muito obrigado, professor Primo, pelas palavras. Agora eu passo a palavra para a professora Lavínia Borges.
Bom dia para todos, professor Abel, Primo, todos os presentes, professores e alunos. Né? Então, em primeiro lugar, em nome do professor Romildo e de toda a diretoria da COPPE, eu quero dizer que me sinto muito honrada de estar aqui e gostaria de cumprimentar não só o programa de Engenharia Química, mas principalmente a comissão organizadora pelo esforço e pela determinação em recuperar e trazer de volta esse importante evento de divulgação científica, não só do programa, mas de toda a COPPE. Eu acho que esse tipo de evento é importante para a divulgação da instituição como um todo, e, nesse momento que a gente está precisando se reinventar, não só tecnicamente, mas também nas nossas relações, procurando trazer de volta nossos alunos para recuperar essa ideia de pertencimento, né, esse sentimento de pertencimento da nossa instituição. Esse tipo de evento é fundamental. Então, eu me sinto muito satisfeita em estar aqui nessa sessão de abertura. Desejo sucesso, né, e que todos aproveitem bastante. Eu dei uma olhada na programação. Infelizmente, a gente, nessa vida que a gente tem na diretoria, não consigo botar na agenda para assistir algumas coisas, mas acho muito interessante que todos participem. Eu acho que dessa pandemia, de tudo que a gente passou, esse distanciamento da universidade foi uma das piores consequências, porque quando a gente faz um programa de formação, seja de graduação, mestrado, doutorado, muito mais do que nossas teses e nossas cadeiras, né, a relação, a troca entre colegas, professores e alunos, a permanência na instituição é muito enriquecedora, e a gente perdeu isso, e a gente precisa recuperar. Então, acho fundamental esse evento, principalmente o fato de vocês terem feito ele basicamente presencial, né? Algumas palestras serão remotas, mas todo o resto presencial. Então, vocês estão de parabéns, desejo sorte e sucesso, que eu acredito que será o resultado desse evento. Obrigada e parabéns novamente.
Obrigado, professora Lavínia, pelas palavras. Reitero meu agradecimento pela palavra do professor Cláudio Habert, do professor Primo Albuquerque e da professora Lavínia, e desejo a todos um excelente 20º Colóquio de Engenharia Química.
Hello. Hey, Antonio, good morning. Can you hear me?
Hello, good morning. Yes, I
Hello,
hear
nice to
very
meet you.
well.
Are you all set there? Can we start?
Yes, I'm also here.
All right. Good morning, everyone. Welcome to the first session in our 20th yearly colloquium. We are thrilled to have Professor Antonio Chanona in our event today. He was very gracious to accept his joining us from the other side of the pond, all the way from London. And without further ado, I'd like to introduce him before he starts his talk. Professor Antonio Chanona is an assistant professor at the Sargent Center for Process Systems Engineering at the Imperial College of London. And his main research interests are on the automation of chemical processes via optimization, machine learning, and control. He has received his bachelor's from the UNAM in Mexico and his PhD from the University of Cambridge, where he was awarded several prizes, including the Danckwerts Bergman Prize for Best Doctoral Thesis of the Year. He also is the awardee for several other laureates, just like the International Federation of Automatic Control, the National Aerospatial Agency, NASA, and the Institution of Chemical Engineers. Not only he is an exponent within his research line, but he's also very active in pursuing teaching and community building activities, particularly for young people from disadvantaged backgrounds, which is something very interesting. And he asked us to kindly refer to him whenever anyone is interested in this particular teaching and outreach activities. So Antonio, in the name of the organizing committee and especially Professor Mauricio, I would like to invite you to start your presentation. I'll just try to fix the mirroring. I'll just ask our technical staff to try to fix it. Just give us a second, please.
Yes, of course. Thank you very much for the invitation to give the talk. And yeah, thank you. Like, it's a great honor to be able to give this talk. Should I begin or should I wait for the mirroring?
Antonio, okay, it's fine now. You can go. You're good to go.
Okay. Thank you very much again. Thank you very much for the invitation. It's a great honor to be able to present. So the talk of today, what I had outlined is to talk first about what is machine learning generally, like just generally speaking. I know many people here might know a lot about it, but I understand that some people know a bit less. So I'm going to talk about what we mean by machine learning. Then we'll be talking about mostly recent developments in machine learning and particularly in engineering. And then finally, we'll be talking about some of the research that we're doing at Imperial College in this intersection between machine learning and chemical engineering. Okay, so again, briefly, I'll start by talking about what is artificial intelligence and what is machine learning. So this is the kind of picture that I always like to show to my students, which is that sometimes artificial intelligence and machine learning are a bit of a glorified statistics. And I think that is partly true. I think there's something a bit more there, but that is partly true. And also that every time that we hear learning in any kind of machine learning context, generally that basically refers to the area of optimization, where you're basically minimizing some parameter, some kind of least squares, or some likelihood function.
Antonio,
so let's just say machine learning.
Antonio,
Yes.
just a moment. We have a problem of displaying your slides. Can you just wait 1 second so that we can fix
Yes,
it?
of course.
We are trying to figure out what's going on.
Let me-
Acontece, pessoal, isso é normal. Apresentações é uma tecnologia que todos estamos ainda dominando, tá? Já estamos bem maduros nisso aí, mas okay, Antonio, can you hear me?
Yes, I can hear you very well.
All right.
Yes.
It seems that you have advanced a little bit. If you could go back.
Yes, of
Okay.
course.
Yeah, that's okay. Okay. Thank you,
Okay.
and sorry about that. We can see
thank
the
you.
slides now. Thank you.
Okay, great. Thank you. Yeah, let me know if anything else comes in. So sorry, very briefly. So today I'll be talking first about machine learning, like what's it in general. Sorry for the scribbles. The mouse is a bit oversensitive. Then about machine learning and engineering. And then finally, I'll be talking a bit of the research that we do here at Imperial College. So I generally like to start the talk by what is artificial intelligence and what is machine learning. And this is just a meme that I like to show, that it's just saying that artificial intelligence sometimes is treating as glorified statistics, and there is a bit of that of truth. And also the fact that every time that we hear learning in any kind of machine learning, reinforcement learning, we're basically talking about optimization, which these are very typical tools as well that I think people in chemical engineering handle very well. Okay, so again, this is a very big picture definition, but basically artificial intelligence is this more, so artificial intelligence is more the high level, very science fiction definition of machines learning to do things like humans, right? So that's what I mean by this picture over here, or these two. Then machine learning, I like to think about that it's a bit more down to earth. Again, there's many definitions about it, and different people say different things, but I think machine learning is more what we actually do currently, which is teaching machines or computers to learn from data, but without us explicitly like stating every single detail. And I'll talk a bit more about this. Throughout this talk, I will generally talk about machine learning and AI a bit interchangeably, mostly using this definition, which is what we can do now and the algorithm that we use. So what is machine learning now? So here's the distinction between what we call traditional computer science, right? Which is that a programmer has to tell the computer specifically what to do. So an example is, let's assume that I'm programming a computer to play chess. Yeah. Then the programmer would have to tell the computer or give instructions to the computer in the sense of if-else rules or loops, where it would say, you know, move the horse to this position if your opponent moves their bishop or their tower to this other position, otherwise move the queen. So it's very specific instructions. For example, in the case of predicting cats and dogs via images, again, maybe you would be very specific and say if the picture has a pointed snout or it is big in comparison with what's around it, it's a dog, otherwise it's a cat. Yeah? So this is what we would use traditionally in computer science. Now, machine learning is now the area where we actually provide examples. So we provide examples, and I'll obviously talk more about this, but the typical examples that we've all seen of cats and dogs. And just by providing examples, then the algorithms are able to learn what's a cat and what's a dog. So just to say, the definition of machine learning actually goes back quite a while, right? So there's nothing anytime new. And there's many definitions. The one that I like most is by Arthur Samuel, which said that machine learning is the field of study that gives computers the ability to learn without explicitly being programmed to do so. Okay, so there's three types in general of machine learning, right? There's supervised learning, unsupervised learning, and reinforcement learning. So first we'll talk briefly about supervised learning. So supervised learning is simply about fitting a curve, right? So the typical example is that we would fit a linear, like a linear regression. And when we use neural networks or Gaussian processes or regression trees, all that we're doing is simply fitting some nonlinear function, right? But the area of supervised learning is nothing, like there's nothing more than using very clever techniques to fit curves to data. So for example, the typical example is, again, if you have a neural network and you wanted to predict cats and dogs, you would give it a lot of examples of cats, but you would tell it it's a cat, right? That's why it's called supervised, because you're telling it the correct answer. You'll give it a lot of images of dogs and tell the computer, these are dogs. Again, you're telling it the correct answer. And then when you have a new example, then the machine is able to, or the algorithms are able to learn this and encapsulate the main properties, and then decide if this is a cat or a dog. Notice that the difference here with respect to my previous example is that here you're not telling the computer anything. The only thing you're doing is providing examples. So that's what we call a classification problem, of course, because then you have a cat or a dog and then it classifies it. That's why it's called classification. Then we have also regression techniques, which, for example, a very simple example that's very common use because I think it has good intuition, is that you want to predict the value of houses. And then you would simply, you have a bank of lots of houses with square meters, postcodes, number of windows, so on. And you give the prices for each of them, right? Then when you have a new house, you can pass it through your neural network. And because it's learned through examples, and basically what it's learned is the weighting, right, of each of the features, it's going to tell you basically an average value, right, of this house. So again, this is a regression technique. Obviously now what we're doing much more is now working into chemistry or into chemical engineering, right? So one example is, for example, predicting molecular properties. So imagine that you have a bank of molecules, and this is actually a simplified example of something that people are, like, it's a very hot area of research, right? So you encapsulate the information of molecules, you feed them into your neural network. By the way, just how to encapsulate or how to represent a molecule is a whole area of research. And then with this, you can do maybe DFT simulations or quantum mechanics simulations in general. And you can get the dipole moments, potential energy, any other kind of properties. And the good thing about this is, again, we do this for all the molecules with very expensive simulations that we've done throughout time. But then the nice thing is that now when we have a new molecule, we can directly test it in the neural network, right? Without having to do that very expensive CFD simulation. And this is obviously particularly useful when we're screening many molecules, right? So maybe if we want to screen millions of molecules, then we could do this very fast. Now, what I want to draw your attention here is that this is nothing but a model, right? And again, many people are very familiar with this, but a neural network is really nothing but a model, and generally we call them data-driven. So we could obviously do the same for a reactor, more chemical engineering example where, again, you might know some first principles, but maybe, generally you would want to model this as a first principles, right? But just to follow the examples, you could also, change reactants, the level, pressure, temperature, and so on, and then get the outlet concentrations either by measuring them or by a model. And then when you have a new thing that you want to test, you would simply use your neural network there. Okay, so that was supervised learning, just some examples and just to frame the context of where we are. And now we were to go to unsupervised learning. There's different kinds, right? But the main idea behind unsupervised learning is that it's called unsupervised because you don't give labels. So when you're doing cats and dogs, again, you give lots of examples and you tell it it's a cat, it's a dog. When you're predicting house prices, you give the house's features, let's say windows, square meters, and so on, and you give it already the price, right? So that it could predict a new example when it comes on. But in this case, what we're doing is we're actually just giving data without any specific truth or wrong example, and just having the algorithm find some structure. So depending on what structure we wanted to find is the algorithm that we're using. So in this case, for example, if we want to do clustering, we would be doing something like that, right? Where we give all the data without the colors, and then the algorithm would automatically find which colors, for example. We could do something like community detection, which is what Facebook, Instagram, Twitter do, which is based on the connections that you have. So for example, if you have let's say that this is the network of your friends. So if they see that many of your friends are connected within many other of your friends, then obviously they know that that is a friend circle. And then maybe WhatsApp, right? Although, they say that they don't check, but maybe they check some of your words. And if there's a lot of football in the words, then they know that this is your football club, for example, or your group of football friends. We can also apply this to chemical engineering. We've applied it. I won't talk that much about it, but these are all algorithms that are also quite applicable. And then one of the typical example is dimensionality reduction, which I think they do use a lot, or we do use a lot in chemical engineering, things like least squares, or partial least squares, or principal component analysis, or things that are not necessarily more recent, but that people use a lot now, which are autoencoders, which are this kind of neural networks, which are good for dimensionality reduction. And I always like to point out that the first time that, for example, an autoencoder was used was by a chemical engineering, and the first autoencoder is actually published in the AICHE journal, right? And then the machine learning grabbed that and started using it a lot. But anyway, so that's obviously used in chemical engineering quite a bit. Okay, and then the last type of machine learning is this one of reinforcement learning. And the idea here, it's a bit from the word, right? So it's about reinforcing good behavior or bad behavior. And this comes from when we, training pets, for example. So when you're training an animal, generally you want to encourage good behavior and discourage bad behavior, right? And then computers, you can do that the same way. If you're interested, we can talk more about it. But basically, if you want a computer to try to learn chess, for example, you would encourage every time that it wins a game, you would encourage those moves. And every time that it loses a game, you would discourage those moves. So for example, a very famous example of reinforcement learning is the following. So there was this time in the 1990s, around 1996, where there was this big game, right, between Garry Kasparov and Deep Blue about chess, right? So Garry Kasparov, the best well-known player of chess, and Deep Blue was this computer by IBM. Yeah, it was also a bit of a flavor of, the Russia versus the US. Garry Kasparov was Russian, and Deep Blue is a company, IBM, by the US. So it was to see if Deep Blue could actually defeat the best player in the world. Garry Kasparov was the best player in the world. So the idea here is that engineers from IBM hard-coded the instructions with if or else statements. So this is not machine learning as we know today, right? This is the original machine learning from many years ago. Actually, people called it expert systems, or still call it expert systems. But the idea is that engineers from IBM talked to many people, many experts on chess, and they asked them, what should a computer do in certain situation? And the computer was basically some kind of glorified lookup table, right? Where given some way in which the board would look like, then that would be captured by the computer and it would make a move, and so on. But the important thing to note here is that these were if and else statements, right? So just very specific. So this final score was 1-1. There's a bit of controversy there. Wikipedia, I think, has a lot of information on this. But basically, Garry Kasparov in the end said that it wasn't a computer. It was a computer also helped by many experts. But the point here is that human and machines were very, very equally matched. Now, obviously, chess is a very difficult game, right? But you would expect machines to do much better than a human, right? So now we fast forward to the 2000s. Yeah, more specifically, I think this is around 2013. And now we have a new game. So instead of chess, we have the game of Go, which is a much more complex game than chess. There's many reasons why, but a particular reason is if you can imagine, chess is a relatively easy game to encapsulate for a computer, right? Because what you need to do is collect pieces from the other side. And each piece is actually worth, some number of points even. And obviously the idea is to get the king in the end, but there's a lot of, it's quite well structured. On the other hand, Go is a game where, without going to too many of the details, but what you want to do is you want to put your pieces around your opponent's pieces. Yeah. So you want to put your pieces around them. So that's a much more abstract thing to encapsulate, right? How do you tell a computer that you actually, whenever someone puts pieces here and there, you actually want to go around it and encapsulate to win those points? So not only is it more abstract, it also has what we call a much broader search space. So it means that the options are much larger. Yeah, and then there was this game where AlphaGo, which is Google DeepMind computer, was going to play against Lee Sedol, which was one of the best players in the world. And well, actually, this was not expected, and there's a very good documentary in YouTube, which is free to watch, about this. But AlphaGo defeated Lee Sedol 4-1. And if you actually go through the documentary, AlphaGo almost totally dominated the games. Yeah. But not only that, because after playing Lee Sedol, it was able to learn from him, and then it defeated the number one player in the world 3-0. Yeah, so the number one player in the world was not able to win a single match versus AlphaGo. After that, what they said is, okay, let's get the 5 best players in the world, right, all in a room. And together they discuss and they decide what move to do. Yeah. And then AlphaGo makes its move, and they go back and forth, right? And the idea is that AlphaGo defeated the best 5 players in the world without them being able to win a single game. And then finally, there was a new edition of AlphaGo, which was called AlphaGo Zero, which actually defeated AlphaGo 100-1, right? And just to say, this was not the same game 100 times, right? So there's an element of stochasticity. These algorithms are stochastic, and they try different techniques to try to beat the other. And even then, just AlphaGo was way superior. AlphaGo Zero was way superior to AlphaGo Zero. So by this point, obviously, there was no computer that could actually, there was no human that could actually compete with a computer. Okay, so how was this neural network, it was a neural network which is called a Monte Carlo tree search, but it was basically a neural network. So how does the neural network manage to defeat all the players in the world? Well, the idea is that the computer first trained in a kind of space jam manner, right? Where it would learn the moves from the best players in the world. So the idea here is that just as in chess, the tournaments are published. So you can see what moves experts play right throughout tournaments. So the computer, or in this case AlphaGo, would be shown the board before an expert made a move and after it made a move, right? And then it knew basically what was the difference, right? And that AlphaGo did by looking at professional tournaments and the tournaments of this. And then he was able to basically encapsulate the knowledge of the best players in the world. This is called apprenticeship learning or behavioral cloning. That's how they call it in machine learning. They generally have this way of making fancy names, but that's how they want to call it. But then also AlphaGo did something that no other machine is able to, no, the human is able to do, right? Which is what itself played, right? So it played against itself many times, trying many different strategies. And obviously the ones that worked best were the ones that it kept. And that's the way that then it managed to defeat any human player in the world. Okay. So that was just the quick introduction of what machine learning is and what kind of algorithms and elements are to it. Now I'm going to talk about some interesting developments in machine learning, and particularly some interesting developments for engineering, right? For us. So the first thing that I want to highlight is that while AI and machine learning is very impressive and it has done very impressive results, it's actually not found a lot of success in the physical world, right? So when experts in machine learning have tried to translate all of this to the physical world, initially they had a lot of trouble. So this is that DeepMind keeps losing money. This was 2020, and then in 2019 as well. Then OpenAI, which is one of the companies of Elon Musk. They disbanded the robotics research team, right? Because actually, well, in robotics, people know that it's not AI or reinforcement learning that solves it, but rather control or model predictive control, techniques that engineers are very good at doing, right? So the first thing is that pure AI, at least currently, maybe eventually, maybe 20, 50 years, things will change. But right now, pure AI will not solve all our problems, and much less the problems in the physical world. Yeah. So there's this very nice review that I liked on, it's in Computer Schem Eng. It's done in collaboration with Dow, and they have this very nice section where it says that it's much easier to train chemical engineers on data analytics than to train data scientists on chemical engineering. And obviously this is done on a chemical engineering journal, but I've seen this repeated many times, and a few times also by data scientists or machine learning engineers, that, they can't do a whole degree on chemical engineering. However, it's very easy to learn how to code. And actually most people like the research scientists in Google, Meta, all of this, they've actually learned through online courses. And many of them are engineers, actually. So anyway. That's the first takeaway. The other takeaway, and it's combined with the first thing that I said, is that now actually there's recently been a lot of good, particularly by DeepMind actually, a lot of good results from them, also in the sciences and engineering. But the key difference here is that they're actually using a lot of knowledge. And if you see generally on their papers, some of the leading authors are actually, in the case of AlphaFold, which was something protein folded, they're actually biologists, right? Or like bioengineers. When they do some reactors, they're also chemical engineers, where they do, and so on. But so anyway, AlphaFold is another very good, it's one very good example of machine learning that actually made it into the physical world. The idea here, without going into too many details, because again, I'm sure many people know much more about this than I do, is that you have a protein, and a protein is just like a very long strand, right? And then knowing how it folds is very important, because then you can see how it behaves, right? And this could help you anything from create different drugs, right? Or how to assess or cure, or at least find treatment or some initial cures for some diseases and so on. So there's this competition where basically they give you a string of proteins, and then you need to say how it folds, right? Based on an algorithm or a computational method. And then depending on how different it is, you get a match and you get some amount of points, right? For doing it or not doing it. And the idea here is that AlphaFold, so this, which was, you can think about it, it's similar to AlphaGo, or it's the name that DeepMind gives their computers, basically, was able to predict point protein folding very, very well. Now, what is the takeaway from here? Well, it actually happens that it wasn't brute forced artificial intelligence, right? So I won't go into many of the details, but basically they put a lot of information from thermodynamics and chemistry into their models, right? So basically what they were predicting were not, for example, were not folds directly, but distance predictions and angle predictions. And then they did some kind of thermodynamical properties matching, and then they did some kind of optimization on it. And that's how they did the prediction of the structure. But again, the main takeaway of here is that this took lots of biology, lots of thermodynamics, lots of genomics, and of course also a lot of machine learning, but without the connection between the area and machine learning, they actually wouldn't have gotten very far. Okay, another typical example is what we call now physics-informed neural networks. So again, as you can imagine, it sounded looking that neural networks were not as good as we thought, particularly in the physical world. And what people are starting to do now is something that's called physics-informed neural networks, which I won't go into too many of the details, but they're particularly good at predicting computational fluid dynamics. And again, this is the idea of combining physical knowledge, in this case with artificial intelligence or machine learning. Reinforcement learning for control. So just as reinforcement learning has been used to play video games, right? It can also be used on, for example, process control, right? So this is the schematic that you have on reinforcement learning for games, right? So first you learn from experts, from demonstrations, then you self-play, and then you put it in deployment, right? This is just the same schematic that I showed throughout different slides. And it happens that we can do exactly the same with a controller when we want to, for example, control some chemical process. So if you think about it, both a game and a process control is what we call a sequential decision-making problem under uncertainty, right? In a game, the uncertainty comes from the opponent. In a process, the uncertainty comes from the process itself, right? But we can have the same schematic. So just as we had, for example, the expert demonstrations by expert players in the case of Go, I mean, engineers are very good at building controllers, like I mentioned. So you can have a neural network learn, for example, the optimal, how a PID controller or even a MPC, so a mode predictive controller works, right? And apply this apprenticeship learning to learn from very good controllers that, again, very good controller engineers have done. After that, you can use some kind of process model. Either it can be either data-driven or first principles, and you can apply reinforcement learning on it, right? To even make it even better than your traditional PIDs and MPCs. I won't go too much into the details. This works particularly when you have very nonlinear processes, and particularly your uncertainty propagation is particularly sparse. So that would be this part of the self-play, and then deployment. And so then you can also apply it then when you deploy it after fine-tuning it, of course, and that's what people call transfer learning. Again, machine learning people like to put very fancy names into these things. So something that then, for example, DeepMind again did was actually control the nuclear reactor with reinforcement learning. And again, this is one of the examples. Again, I won't go to too many of the details. This is published in Nature, but it's as well how they apply control engineering to a specific system. But again, it's with a lot of knowledge from engineers that do not have to do necessarily with ML. Okay. So brief takeaways from this is that there is still a lot to do. Yeah, so the use of machine learning in engineering, and in particular in chemical engineering, there's still a lot to do. And it's a field that it's just getting started. The important thing is that merging physical, chemical, and biological knowledge with machine learning or data science is the way forward. Right? That's the way that we found that we can actually do progress. And the final takeaway is that it's actually not hard to transition from engineering to any machine learning applications, right? So most, learning data science or machine learning is quite simple. So we actually published an industrial data science paper. So my group, along with a group in Manchester, and two companies, so JMP, which is a statistical software, like a machine learning software, and Solvay, who's a chemical company, where we talked about particularly also machine learning applications in chemical and process industries. This is a less academic paper and more applied paper to industry. So actually, what of these techniques of machine learning we're currently actually using? Obviously, generally on research, right? We try to be more at the forefront, and we use more complex techniques because that's what maybe industry will use in maybe 10 or 5 or 20 years. So this is a very applied, but here, if people are interested on how on what things you can use of machine learning in the chemical industry, we try to put this together. Okay, now for the last part of my talk, I hope people aren't too overly tired. I'm gonna talk about now my group and what my research group does, and which is again mostly merging machine learning with chemical engineering, but not just substituting machine learning with chemical engineering knowledge. Okay, so this is my research group. So we call optimization machine learning for process systems engineering, and we do a variety of applications. Here I have most of them that we like to do. And today it'll be a bit brief, but I'll be talking about a few of them and how we use them in conjunction in a few problems. So mainly, just to start with, I'll be talking about these 3 projects. So data-driven optimization, automated first principles model construction, and digital twinning. I'll spend most of the time on data-driven optimization, and then the others, I'll just mention them briefly just to say what kind of research we're doing in this area. And so this first part is more about optimization, and then the second part is more about model. So data-driven optimization. So the first question is, what is data-driven optimization? And this is the big picture idea, that I want people to have in their minds when I'm talking about just what data-driven optimization is, right? So which is some kind of algorithm that it starts with some samples, and then it makes its way onto the optimum slope. Yeah. So what would be a big picture idea again of this? Let's assume that we have some objective function here. So this is an optimization problem that we want to solve. This might be some kind of model on some kind of, some mathematical abstraction of a real process that we're trying to solve. And the idea is data-driven optimization is used when we actually do not have the form of this problem. Yeah, so we can only sample it. So imagine that I can sample this problem, and I can get, based on a variable x1 and x2, I can get what's the objective function value. Yes, but I don't know the form, so I don't have derivatives. I can't plot it. I can't visualize it. And that's why we say it's a data-driven optimization, right? Because we can only sample. And we'll see that we have lots of examples of this, but this is just to start the framing of the problem. So again, the idea is that we don't know the shape of the function, no derivatives, and we can only sample, right? So I can only take samples. I can decide a value of x1 and x2, and I can evaluate that function, and that will give me the value, right? And then the idea is, okay, I have this, let's assume that I have these 4 points. So how do I select my best point, right? Assume that each of these points is maybe an experiment, or maybe a computational fluid dynamics simulation, or maybe a quantum mechanics simulation. So these are very expensive data points to get, right? So I cannot just randomly use them. I have to have some way of actually going forward, but without taking thousands or millions of steps. And the idea here is that there's many ways to do it, but one of them is that we try to approximate this function, which we don't know the form, with another function based on the samples that we have. And our intention isn't to do some sampling intelligently so that we find our way all the way to the optimum. Obviously, this is an easy function. Generally, you have lots of challenges because your function might not look as nice, and they might be a bit different. But I won't go into too many of these details. So some examples problems of data-driven optimization. Many are these, right? So this is just to say that these are some examples, but we have actually lots of problems like this. So some of them can be computational fluid dynamics simulation. Again, these are very expensive, and generally simulating it, one takes in the order of hours. So you can't just sample everywhere. The same for molecular dynamics simulation, generally when you want to do it for molecular discovery. Design of experiments, right? So when you do an experiment, you're actually taking a good part of a day, right, to get one sample maybe, or maybe you get a few samples for a whole day or something. But these are very expensive. Model building itself can be thought of as a data-driven optimization problem, and actually controller tuning. Yeah, so for example, what MATLAB does to tune its controllers in Simulink is a data-driven optimization approach, actually, where it simulates, it gets the answer, and then it tunes it a bit, and then it simulates again, and then it minimizes the discrepancy between the trajectory and the set point. Okay, so within this, there's what we call surrogate-based optimization, yeah, or what people call model-based derivative-free optimization. So assume that we have these samples. Yeah. So here I'm just in one dimension, just because it's easier to visualize. So I have x, and I have the function f of x. So these are my data points. And then what I can do is I can try to fit a function to this, right? So again, I don't know what's actually my function f of x, right? But I can definitely fit a function. And then this function that I fit, this I can actually optimize using derivatives or any other kind of algorithm that I want, because I do have the functional form, let's say, like the actual equations for this function. Yeah, but then building this function might be problematic, because how do you choose a function, right? So depending on the function, I mean, inside, when you're interpolating, generally it's going to be relatively okay. But outside, you really want to choose a function that resembles well your true function, which you by the way don't know. And another thing is, where is the function valid, right? Again, and this is where we'll talk about later, that we use trust regions. So generally, you want to define where your function is valid, particularly if you're using optimization, right? There is a saying that says that if your function has an error, your optimizer will find it, right? And the idea here is that, again, you always have to define, whenever you have a function, particularly like this ones, which are like what we call just a data-driven model of your objective function, you want to have some area of validity, right, that you have. Okay. So what I'm going to talk about is Bayesian optimization with safety trust regions, which is something that we're working on, and we're actually using it to do a few chemical engineering applications. So first of all, I'm going to talk very briefly about Gaussian process, which is a machine learning technique. Yeah. So I'm not going to give any mathematical equation about this, but I'm just going to give the intuition. So let's assume that you have some training data. Yeah, you have some data that you collect. You could always fit some kind of function, yeah, to this data. And this would be like a neural network. So this is not a true function. This is maybe your neural network, right? And then given a new value of x, then you can predict a value of y. Yeah. But notice that you actually don't know what happens from here to here, right? This is just the best guess that you can give. Well, the nice thing of a Gaussian process is that it also gives you an uncertainty, right? So in this case, notice that close to where I have points, my uncertainty is very low, yeah, because I have a point near there. But for example, here where I don't have points, right, my uncertainty is very large because my model says, well, I can say it's more or less around here, but actually it can be many other places, right? I just don't know. And the Gaussian process is a regression technique which actually does that, which builds a mean function, but it also builds a confidence interval around it. And therefore the prediction, so let's say that I want to find a new point x new, then this tells me the prediction is not only my mean, so this would be my mean, the same point that I had before, but it's also an uncertainty, right? So it gives me a Gaussian distribution with a mean and a variance. And that's very useful, particularly when you want to predict things, but you want to be careful, right? So for example, if you have a reactor and you're very careful of your temperature, maybe you want to have not only a mean prediction of your temperature, but also a standard deviation. Yeah, and then you want to be careful with this. So anyway, this is a technique that we use a lot, particularly in engineering, because also Gaussian processes, without going to too many of the details, it's also a good with low data sets. So now I'm going to go to Bayesian optimization. So the idea of Bayesian optimization is a data-driven optimization technique. So before I talked about data-driven, and here Bayesian optimization is one of those algorithms where I want to optimize some function. So this is the function that I want to optimize, right? So let's say it's just 3 peaks, yeah? And I can only sample the function, yeah? So for example, notice that if I sample the function here, 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 and here, I get this image on the right, yeah? Where I have also my data points, yeah? But then I build a Gaussian process model with this data. Yeah. So the idea of Bayesian optimization is to build a model of your objective function, similar to what I did previously. And then what you do is, because this is your function, you actually optimize the mean function, but you give a bonus for exploration. So what you want to do is you want to sample the most promising points. And the way that you do that is that you optimize a mean function. So in this case, I'm optimizing this mean function minus, because I'm minimizing, yeah, these a penalty, or sorry, in this case, a bonus for exploration. So I'm minimizing this area down the curve here. And my idea is that I want to find finally the answer to my original function. So without going too many of the details, this is how it would look like. So this is my same function that I had before, right? So if you see, this is my function with three minima that I had before. I just fitted a Gaussian process to it, and I evaluated. And notice that the curve below, which is my mean value minus a bonus for exploration, is this point over here. Yeah? So then this is my minimum point. And then what I do is I sample that point. So this point is my minimum. I sample it, and then it gives me this point, right? So I thought it was a good point, but it actually ends up not being such a good point. Then my next best point is this one over here. Again, I sample it. It ends up not being that good. But notice that I'm also exploring my function, right? As I go along, I'm exploring the function. So this one over here is the next one, and I sample it there. Then the next best function is this one. But now notice that my function has become very multimodal. Right? So it's not only non-convex, but it's multimodal. So it has many of local minima. So then the problem is that I have a local minima, so I will sample there. Now that's again my global minima, but this is again my local minima. I'll sample here again, and so on until I finally manage to sample here. And here I've optimized my function, because in the end, this is my lowest point. And then I say that I'm finally done, because there's no other better point inside here. Now, an idea is that also Gaussian processes are hard to optimize. So generally what you want to do is have some kind of evolutionary algorithm like this one, which actually optimizes your Gaussian process itself. And that way you can actually hit the best, basically the global minima. Obviously you can't do it for sure, but it's a good empirical way to try to do this. Okay. So without going into too many details, there's two disadvantages. So what I've just shown is what we call Bayesian optimization, but this has two main disadvantages. One of them is that Gaussian processes do not extrapolate well, right? So we have this problem of, okay, you can fit your points over here, but then what happens outside this area? And then what we do is add something that are called trust regions. Yeah, so remember that, for example, if we're actually optimizing things in chemical engineering, so like reactors, you want to be very careful with optimizing temperatures or pressures. You don't want your reactors to explode, right? Or even just not to be in unsafe operations. So then what we do is we have what we call that trust region, which basically gives us what is known as a model adequacy ratio, which is the ratio between reality and prediction. Yeah. So this tells us how good our algorithm is doing. So when our algorithm makes a prediction, we move to that new point, and then we check, okay, how good was that prediction? And that tells us how good is my model, and then my trust region shrinks or expands based on this point. Notice now that on this plot over here that I have, my algorithm starts with a low trust region. It actually expands, right? Because it becomes more confident, because it's saying, well, my predictions are doing very well. So I'm actually expanding. And a nice thing of this algorithm, which I'm not going to go into too many of the details unless people are curious, then it actually, once it finds an optimum, it zeroes down on it, right? And this is an automatic thing that it does. The algorithm does it. This is not something that, I mean, this is our techniques that we adapted, but this is very well known. These are what's called trust region methods in optimization. But then you're also able to know that you find an optimum, because again, you can't really visualize the function. If people are interested, we also have a paper on this, which I guess I'll share the slides. If anyone's interested, they can learn more of the details here. And then that's the main idea. So then this is the main idea, like the big picture idea. Here on the right, you have what the algorithm is looking at, actually. And on the left is how it looks in general. Now, something to keep in mind here is that we're also particularly interested on, for example, not violating constraints. So in this case, we want our function not to go beyond this line over here. And notice that the trust regions are very useful, because if you look at the right-hand side, at the beginning, your constraints are very wrong, right? Then they get refined relatively quickly and quite well. But the trust region helps us not violate those constraints early on, where we actually don't know what the shape really is. So again, the idea here, I mean, this is a very big abstraction, but think about when you're optimizing some kind of reactor or system that can be unsafe. Another thing is, okay, this is only data-driven so far. What happens if you actually have a model, right? So I made a big deal about models and how knowledge is important, and here it seems like we're only using data. But actually, if you have a model, this works even much better, because then you have what we call a discrepancy model, where you have some model, like a knowledge-based model, some maybe kinetic equations for a reactor. So this is what we call an imperfect model. But then we all know that all models are wrong, right? But some are useful. So in this case, we can use our model, where this part is the discrepancy term, and this part we're going to model as a Gaussian process. So how do we do this? Well, now our data points that we had before, now they're measurements, right? So this y is my measurement, and then I compute what my model tells me at this point, and that's what I called y model. And then each of these points is actually an error, right? This is the error between my measurement and my model. Yeah. And then I can fit a function the same way that I did before. And now for a new condition y, yeah, and maybe u here is maybe some control parameter, I now can give an error estimate, yeah? So I give an error estimate of my model now. And then in the same way, again, for a new input, I have a normal distribution where I give an estimate of my error, but also an uncertainty of my error. Yeah? And then what I can do is that discrepancy model, I just put it over my imperfect model. So notice that I'm doing this exactly, right? So I'm taking measurements, seeing how wrong my model is, and then adding this Gaussian process as an error term to my model. And then again, actually this was computed with my error model. So that's a full picture of what we've been doing here. Okay, I won't go into too many details of this because I think it's a bit repetitive, but the idea is that we've used this for reactor geometry optimization. So I'll skip some slides now, which are not super important, but we're presenting this at NeurIPS, at a workshop in NeurIPS, which is one of these, like a big AI conference. At one of those workshops, we're giving what we did here with a combination of AI and CFD simulations. So I'll skip over these slides. And just very quickly, I'll go through the modeling part, where I talk about automated first principle model construction and digital twinning. And this I'll be quite brief, so it'll be much shorter. So the idea is we're trying to work on, so all of this is a bit work that we've done, but also work on the development. So here we have automated first principles model construction. So for example, sometimes we want to build models automatically, right? So obviously we have lots of scientific and engineer experts that are very good at building models. But what if we could have an automated platform to construct kinetic models, also only giving data? Yeah. And what we have here is two techniques. One, that it's an automated kinetic model generation. Yeah. So is that we want to give knowledge based on our kinetics. So for example, maybe we work with a chemist and the chemist says, okay, this reaction that is happening is only a second order reaction. So we don't allow any terms that are above second order. Yeah. And then what we do is we have another model selection. So once we create lots of models, we have a model selection model, which actually tells us what is the most statistically probable model from all the ones that we have. So how the framework works is first you have a kinetic model generation tool, which again generates lots of models. Then you have to do some parameter estimation. This is just always what you have to do with models. And then you do a kinetic model selection, which again, from the models generated over here, it just selects the most probable models from a statistical point of view. So looking briefly at the kinetic model generation tool, the idea here is that we use a technique called branch and bound. I'm not going to go into too many of the details, but basically, you know, we have different expressions and we generate different models and so on and so forth. Or something that we also use is something called symbolic regression, which is a kind of genetic algorithm done for how to create different models. Again, I'm skipping over the details because I know it's a bit dense in terms of detail, but the idea is that you can generate many different models via some kind of genetic programming approach. Then the parameter estimation. Well, here we use what just everyone knows, that we maybe when we wanna do parameter estimation, we want to estimate the best parameter models, right, that resemble our reality. So we want to minimize the difference between our reality and our model, and that is basically an optimization problem. So what we would generally do is some kind of stochastic search algorithm, something like a artificial bee colony or a particle sort genetic algorithm. And then we use a gradient-based optimization technique, generally something like BFGS, which is a kind of, it's a quasi-Newton method, so very similar to a Newton method, but it only uses first-order information. And this is something practical. There's nothing very theoretical behind it. It's just for practical reasons. And finally, the kinetic model selection. So let's assume that we have a lot of models. Yeah. So now we've generated a lot of models with this, and then we've estimated the parameters. And we want to know what is the most statistically significant model. And then what we do is something called information criteria, which you don't only minimize the squares, right? So this part over here would be your typical least squares estimation, where you estimate, you know, the difference between, so this would be my reality, this would be my model, and I estimate the squares, right? The least squares, I minimize this. So this is again my reality, maybe for my product B. This is what my model predicts. I then minimize the squares of that. Yeah. And this is what I call the negative log likelihood. It's just how similar is my model and my reality. And then what I do is I'm going to penalize the number of parameters. Yeah. So I'm going to say, because otherwise what you end up with is models that are very over parameterized, right? You have many parameters. But here what I'm going to say is, if I want to add a new parameter to my model, you'll have to pay for it. Yeah. And many people do this empirically, but the idea here is that these techniques are actually based on statistical frameworks, right? Like, for example, Bayesian information criterion is just based on using like a kind of simplified Bayesian parameter estimation. Then the Akaike information criterion is using something minimizing what's called the KAL divergence. That's a measure of how different two distributions are, and so on and so forth. But this is basically a statistical way of determining which is the best model. And this we minimize the model. So the idea is that with this framework, which again, we have some results, but we're still working on them, it will allow us to give, to suggest models to our researchers, right? So a chemist, you would be able to suggest it in a couple of minutes, some good models that are also statistically probable. And this is a tool that we're working with some friends that are chemists. And then finally, the last thing that I'm going to talk about is combining first principles in machine learning. So this is basically what people call digital twins and sometimes hybrid modeling. They're a bit two different things, but generally for digital twins, you use hybrid models. So the idea is that we all know this thing between overfitting and underfitting, where if you have too many parameters, so what I've mentioned before, you will simply pass through all your data, but probably this data, this fit is not great, particularly when you're extrapolating, because if you're extrapolating, it'll look very strange. And you have underfitting like this one, where probably your function is a bit different, right? I mean, maybe it's close, but it's a bit different. And you want to balance these two things. So then what people generally do is they have this first principles model, like we talked before, where you have a model, and then you want to have some kind of error model, right? Now, the nice thing about first principles models is that they can extrapolate, right? When you build a first principles models, you generally know what assumptions in the sense of biology, chemistry, physics go into them. So you know what domain it can extrapolate. However, when you have a data-driven model, it cannot extrapolate at all, right? And then the idea is, how can you build a hybrid model that has the best of the two worlds, right? So which can extrapolate, right? But that can also fit your data very well, right? Which is where the data-driven part comes in. And the idea here is that we do something very similar as we did before, where we try to find statistical techniques that allows us to construct the model which best balances the knowledge, right? So the first principles and the machine learning aspect, which is the data-driven. Okay, so that's the end of my talk. I know it was maybe a bit dense, and I started maybe very vague to going to some very specifics. But again, thank you very much for the invitation. It's an honor to be able to give this presentation. And the last takeaways are the same ones that I mentioned before, which is this area of machine learning and engineering. I think it's just getting started. There's many cool things to do here. And, it's very easy to transition between machine learning and engineering. And again, thank you.
Thank you, Antonio. Can you hear me once again?
Yeah, I can hear you very well.
All right, thank you. The floor is opening for questions. Don't be shy. Any of the students first, before Professor Mauricio? Any one of you guys want to ask something for Professor Chanona? All right, so Mauricio.
Well, first of all, I would like to thank you, Antonio, for accepting to be with us today in our colloquium. Thank you very much. And thank you also for the very nice presentation. I think it was kind of a class that many of our students have had the opportunity to learn a bit. Some of them are from other areas that not PSE, you see, but you gave a general introduction, and then also the applications, data-driven, optimization, that are more specific, but some of them work with this kind of study. So Thank you very much. I'd like to make a first question, a bit more thinking about that people that are from other areas. If you think about the industry now, what would be the kind of applications that machine learning could provide immediate, you see, results? That, for example, you have the techniques, you have the data, and what could be examples that could be used? And if you think that those hybrid models could be the next challenge, thinking also about industrial applications. That's it.
Yeah, so I think, so I think in terms of application, so I've talked somewhat to people from industry, and mainly they like the part of anomaly detection or soft sensors, which is, but soft sensors is like building a model, right? That's just what it is. So people from industry particularly like these parts, or the data analysis. So in industry, they have a lot of data. They generally don't have very rich data, right? Because, for example, if we have a process, it's generally around some very specific data, operation condition. But they generally do have a lot of data, and they can do a lot of statistical analysis on it. So these, there's this software, again, I mean, I mention it because I think it's very simple to use, not because I've worked with them a lot, but JMP, which that's why they specialize on actually building statistical techniques, which is, statistical techniques is an in-between between machine learning and more traditional statistical tools. But there's a lot of that, particularly, again, in fault detection, anomaly detection, soft sensors. Now, people who work on other areas, I think generally if people work on any kind of modeling, generally the kind of hybrid modeling is very useful. So that's one part. Now, a company that I work a lot with is BASF, and they work a lot on digital twinning, right? So what they want is they have some kind of reactor, and they want to have a digital twin is like a very clear mathematical model, but that people can also visualize of that reactor. But then it's particularly useful because what they want to have is some kind of, or what other industries as well want to have, like Solvay, for example, is a kind of store where, for example, if I'm an engineer that's trying to construct a new process, I want to go to, like, let's say an app store within my company, and I can grab, I like this reactor, right? And how does this reactor interact with this distillation column? So it's like a kind of Aspen flow sheet, but much more precise, right? So you can actually build very, let's say, very precise flow sheets from the beginning. And that's where I think hybrid modeling helps a lot, because then you can have models that are very accurate, but at the same time, they use the process data, which in industry, they do have quite a bit. Again, we can use all these in experiments. So that's what I would say in general. I don't know if that, I think it was a bit broad. I can zoom in more specific parts, but I would say like a brief, broad first answer. That's what I would say.
Thank you, Antonio. Thank you. Anyone else? Any more questions for Antonio?
Congratulations, Antonio, for the very interesting opening talk. Allow me to speak in Portuguese, just to provoke the student. Gente, quem quiser fazer a pergunta em português mesmo, não hesite, a gente traduz. Esse tema é bem amplo e pode suscitar vários tipos de perspectivas ou questionamento. Então, não hesitem em perguntar. Então, o que eu vou fazer agora em inglês é manifestar minhas preocupações. So I just told them that, do not hesitate to ask, even in Portuguese, that we'll translate.
Yeah, I can almost understand it. Thank you. Yeah.
Okay, I am, what I should say, the older generation of chemical engineering, in the sense that machine learning and the question you just explored here are kind of a new challenge in my perspective. So I have two kind of questions. You said we're just beginning, This is just the starting of a new science, What would be, say, the goals for a 10 years perspective, what we want to achieve. And my second question is related to this one. When we see machine learning, and then you said immediately, this is linked to artificial intelligence, there is no way to avoid the question of robotics and human substitutions. You must be very aware this is a normal question.
Yeah.
So when you look at these things and we say, hey, in 20 years, no longer humans will be needed in industry. Well, we'll have a lot of new things, of course. But then how about human substitution? The decision-making process is a very important aspect to see now. What we do nowadays in company, in big strategic decision, we have decision tanks, people, think tanks. You sit down, 10, 20 experts, and then we discussed about the possibilities. Will this be substituted in 20, 30 years? If so, we have drawbacks to watch out, not to allow things, of course, happening, say, like science fiction always have tried to show us in the past 100 years, all kind of terrific things we would like to avoid. So in a sense, this new generation you're representing, you have a big challenge. In one sense, say, here are the fields where we have got big progress. For example, you showed us one, protein unfolding. I think this is a fantastic field because what will happen in the health and drugs business, there is no way to say we must go and avoid time-consuming experiment, as you said. I see this is really a very challenging field. But on the other side, you say, well, will we have jobs for these growing people in the next 20 years? So please, I would appreciate your comments.
Yeah, no, I think that's an excellent question. And I think it's always a nice question to try to answer. So I guess maybe it's obvious that I don't know the answer. But if I were to try to guess, part of the answer is that I think in 20, for example, in 20 years, so that's my guess, we still will have a very similar landscape as we have today, where we're still trying to really merge artificial intelligence and engineering. That's my guess. Obviously, things will evolve more. But just as we had, I mean, this is, I think, like the third wave of AI, right? It's the biggest one, and one that there's been very big changes. Like now it's the first time that actually tech companies are the most powerful companies in the world, which had never happened before. But we'd already had like waves of AI. So I think, let's say in 20 years, I think we'll still be in a similar domain where we're still merging a lot of engineering with, or biology, let's say, or physics with AI. And I think until then, again, this is just a guess, but we'll be relatively safe from everything else, all these post-apocalyptic things. Something that I'm sure many people are aware, but I'm a big fan of Yuval Harari. You all know Harari, who talks about that the big challenges, at least initially, of AI will be just the displacement of workforce, and particularly robotics, where some parts of manufacturing will be replaced and so on. And I think that's a big problem, but it's not the intellectual part yet. So I think that's the outlook in 20 years. And again, obviously, this is just a guess, and my guess is probably as good as anyone's, and much less than other big experts. And then I think, but I do think like in maybe an outlook of maybe 100 or 50 years, then we will start to go where machine learning will replace practically, or start replacing all these other think tanks, right? And actually more the cognitive parts. So there's lots of research in that area, right? I think that's something that has always more or less been done, but I think now there's a lot of merging between neuroscience and engineering or artificial intelligence. So I know that's being pushed very hard. And I think that, in my opinion, that horizon will happen around 50 years, so from 20 to 50. And I do agree that that's where we have to, well, I think I think we're starting to do a lot of that. So right now there's a lot of fairness in AI, like it's a big field now. Explainable AI, because again, right now explainable AI is more on, okay, you did the decision, tell me why you did it. Because maybe, if a bank revokes your credit card, you need to say why. Or if it thinks that someone will do something wrong, it needs to say why, not just because it thinks, like the algorithm thinks so. But I think those areas are in a good time where they will start to evolve as we progress as well. And then eventually we'll be able to put checks and balances on machines. At least that's a bit my hope. But I think we're in a good path in that sense, where those areas are co-evolving also with the area of machine learning and artificial intelligence, and that we're going to be able to manage it more or less well. That's at least my hope.
Antonio, how is your time budget? Do you have time for another question?
Yes, I do.
All right.
Yes.
Professor Argimiro, just thank you.
Thank you, Antonio, for your nice and didactic, illustrative presentation for this broad audience here. Okay, very, very nice examples that you show us, and some analogies that's important to understand some difficult areas. One of my questions regarding to what you mentioned, that's a well-known statement, that is easier to teach a chemical engineering to learn data science than to teach a data scientist to learn chemical engineering. What is your opinion about put these subjects in the undergraduate courses for to form new engineers with these tools, or they can go after finish this graduate, goes to the Google and learn by themselves to do the data science? This one, I want to see your opinion about that. And the other thing is, what you think about these waves? Now, do you have I think the first machine learning wave was 30 years ago, and then wave goes up and goes down quite fast. And some of that results stay in the industry, but quite a few applications of the machine learning in the industry. Now you have, as you mentioned, it's a bigger wave now. I think we are still growing in this wave, not on top yet. But what's your opinion about this wave? This go down again and it disappear, and all this boom about the machine learning. What will stay in the industry for this new scenario?
Yeah. No. Thank you. I think those are things that I really like to talk about. So in terms of coding or machine learning in undergrad, my opinion is that it should definitely be done. So now in Imperial, we started a course in machine learning. It's in the 4th year. So we start the course in machine learning in the 4th year. And although we teach undergrads MATLAB, students have been struggling a lot, actually. So there's many students who learn Python by themselves, and then the machine learning course is very good. They're able to do the machine learning course very good. But I think in my opinion, there definitely needs to be an element of programming, and programming, not only MATLAB, but something like Python, Julia, C. But my preference is Python, definitely, but any programming language earlier on. Because obviously my opinion is very biased, but I think that these courses are going to be more and more. And now we start to see that almost any industry also asks for some data analytics person. So in the chemical industry, they want data scientists, but also very chemical engineering data scientists who understand things. And so on. So yeah, sorry, long story short, I think it's definitely a good idea to put it in the curriculum. Probably start as early as possible, because I think most curriculums will have a machine learning course at some point, or a data science course for the very specific domain, right? But then I think knowing how to program earlier is super important. So that's my thought. And I think the good thing is that you can give a very general course, just enough that everyone knows, but then very interested students would go and learn more about it online as well. So I think that's for the first part. And then for the second part, so I had on the top, what was the second question?
About the waves, the machine learning waves.
Yes, the wave, yes. So yes, I've had a few talks. I'm sure everyone has had talks people about this. So I think there's two things that are different this time. One of them is more a consequence than a reason, but one is that now, like, actually the biggest companies are now AI companies, and now we've reached the point where people can be the product. Which is probably, it has good and bad sides. But I think that's the main difference, that no time before did everyone have like a computer or a phone or an iPad. And now we do that. So I think for me, that's been the biggest game changer. That not only research, right? So now any people who decides to do a computational PhD will have their own computer. And then it's so much more power, right? Because just everyone is able to make decisions, everyone's able to code, everyone is able to do this. And we also all have digital tools like cell phones. So I think those are the biggest game changers. The fact that we have now personal computers and phones, and that's the big game changer. And that has propagated into this thing where now tech companies are the biggest companies. Now apps are very important, right? So there's a whole industry about apps, and AI is very built upon apps and all of these things. But I think the biggest difference is that we all have personal gadgets. So yeah, I think that's what's changed.
Thank you, Antonio. We just have a final question, if it's fine by you, from one of our students. Is that okay?
Yeah, of course,
All right,
of course,
thank
yeah.
you.
Hi, Antonio. Very nice presentation. Thank you very much. And I have two questions, actually. One of them is applying new technology is not an easy job. And sometimes you have a very well-established technology or very well-established process. So do you see any resistance regarding plant employees or plant operators to apply this technology? And the second one is, how far have we gone in the use of machine learning in real processes? Are we using reinforcement learning in control loops already? I think virtual sensor is much more common, but how far have we gone in real processes?
Yeah, no, those are two excellent questions, I think. So the first one about is there resistance? Yes, definitely. I mean, like every time, like on everything. But I think, for example, it's very well thought out resistance. So, for example, process operators, they will not change the set point, right? For example, of your plant, unless they know exactly why. So my group is not doing research on that area, but there's other groups that are doing lots of research on that area of the same thing. So how maybe some kind of optimizer that also tells you why it goes to that set point, or that explains why. And that's, again, the area of explainable AI. And broadly speaking, there's two kinds of algorithms. There's the ones that are simpler, and that then when they make an action, you can understand why. And then others are those who you have an algorithm, which is very powerful, right? Because with explainability sometimes, and I'm generalizing, but sometimes you have to limit the power, let's say, of the algorithm. But other things that there are is that you have an algorithm, but then you have an algorithm on top of that, which is like the translator, which sees what that algorithm does, and it tries to translate that into a human operator. And in chemical engineering, we've always had that, and that's the control boards, right? So the control boards are the ones that the operators look at, and they actually see what's going on in the plant. And that's always been more or less based on, so, principal component analysis is something, it's a statistical technique. At some point, people in machine learning decided to say that PCA was machine learning, which is, a bit dubious. But anyway, just for the point, I think there is resistance. I think there'll always be resistance, and I think we'll slowly get there. But I also don't think it's because the operators are wrong. I think actually the operators help us a lot in managing this change slowly. Because, if there was like a big explosion of a plant because of AI, that would, any progress that you would have would just be set back by a lot. But because operators know their job very well, then they help the transition be a bit slower, but in a safer way. And then the second one is how far are we? I think we're still starting. So there are examples. So companies, again, like BASF, like Siemens, they do use AI, and particularly models and neural networks. They do use neural networks, but they're just starting. And I think, again, real research into this, I mean, again, there was like a peak at some point, but then it dialed down. But then maybe we started in 2013, 15. And it generally takes time to permeate onto process plans. So it will take time. And that's for reinforcement learning control. So I worked a lot on reinforcement learning control. I think it's a very cool area. But I think, you know, the control theory and control, model predictive control is just so good. I also work on that area and I like it very much. That there, it will struggle. So control engineers are amazing, right? And they're very good and they know the things very well. So I think that might take a while, and maybe we just simply end up using MPC, so model predictive control, all the time. But I think it's still something worth exploring because it might not. There are some good things that reinforcement learning can bring to the table, but I guess we'll have to do some more research to find out.
Thank you, Antonio. Just I promise you the final question. It's because it's a question from one of our students. So
yeah.
Just wrapping it up.
Yeah, no, of course. Yeah.
Thank you, Professor, for the great lecture. One of the things that might happen in AI applications, and especially in the oil and gas industry, is that sometimes there is too much data, and part of this data is faulty or needs to be reconciled. Mm-hmm. So I wanted to ask about your thoughts on the preparation of data and the treatment of data and the reconciliation of data before inputting the data into the machine learning models. What are your thoughts about that?
Yeah, I think I won't have super interesting or different thoughts about it. Data treatment is a huge thing, and it's the thing that we do less in research. Because in research, right, because we want to highlight a very specific part of the problem, we assume that the rest is perfect and ideal. So we generally assume that data is ideal. But the area has been growing a lot, right? So all these MLOps and pipelines. So for example, I can see that you're very familiar with industry, right? But when I talk to people from BASF, they tell me, well, you know, the machine learning that you're working on is this little piece, but there's all this other pipeline that we're working on. And industry is very interested in executive education, right? So where their engineers are taught, so their managers are taught and their engineers are taught how important all this pipeline is. So yeah, so I think I didn't say anything new there, but I just think it's super important. And in research, we don't do it as much. I think it's reasonable because we want to delve into other parts, but it's definitely a very important part. And, you know, without that, nothing else would work. Yeah.
Right. Thank you once again, Antonio, for your talk, for replying to the questions, both from our faculty and as well as importantly as from our students. So let's give it another round of applause, please, to Antonio.
Thank you very much. It's been a pleasure and an honor to be able to
Thank you for joining us. You certainly enriched our event. So that's the finish of our section. So thank you.
Thank you. Thank you very much. Bye.
Pessoal, só reforçando o convite, a gente vai dar um recesso agora até as 14 horas, a gente volta com a plenária do Dr. Harry Westphal, diretor do Laboratório Nacional de Luz Síncrotron. Então, trocando o tema, assim como o Habert prometeu. E logo em seguida da sessão das 14 horas, às 15h30, a sessão de exposição dos temas, né, a nossa dose de ciência, vai ser conduzida por vocês, na verdade, né, pelo nosso corpo discente. Então, a gente se vê às 14 horas. Obrigado.